Hello, Tensor friends. By special request, is the covariant derivative a tensor? Very exciting. There's two ways to do this. One is the traditional way, as I guess you would have on homework or an exam. And the second one is just kind of a logic way. So I'll show you both. Okay? Okay. So we have an arbitrary vector that can be expressed in a linear combination of its components and its basis vector. So we just want to review very quickly what the covariant derivative is. So we're all on the same page. Okay, if we take the derivative of that vector with respect to an arbitrary, the coordinate, we use the product rule, first times derivative of the second, plus the second times derivative of the first. And then we have to deal with whatever this is, the derivative of a basis vector with respect to a coordinate. Okay, and that turns out to be a definition. So the derivative of a vector is a vector. And we can express that as a linear combination of its components and basis vectors. And this component turns out to be called the Christoffel, the symbols. And you can see how we followed the indexes. So you've got two covariant indexes, I and j. So you have to keep those straight. And then you're going to need a summation index here because, as an example, in 3 dimensions, this would represent 9 terms. Okay, so that's why we have a summation index here. So let's put that right back in here like that. Okay, so this went right back there. And now I'm going to do some swapping of the summation indexes, the dummy indexes. So I'm going to swap i's for k's. Do you see what I did? K's and i's. I swapped them. Now I can factor out an ei. And in doing so, now I can put a bracket here, and this piece is defined as the covariant derivative. Okay? And what it is the generalized form of the partial derivative. So as an example, in Cartesian, the coordinates, we know that the partial derivative of a basis vector with respect to a coordinate in Cartesian, the plane is 0 because these are orthonormal basis vectors, so they're constants. So the derivative is 0. So there are no Christoffel, the symbols. So the covariant derivative is the same as the partial derivative in Cartesian coordinates. It's not true in the coordinate frames. Okay? So how can we show that this is a tensor? It's the same, the format you use anyway. On any tensorial, is that a word? Tensorial? I think it is. On any tensorial equation, right? So you have some equation, and the first thing you do is you look, how many of the free indexes do I have? So you look on this side and this side. And when something is over here and it's not over there, it's not a free index, right? So you only got 2 free indexes. That means you need 2 Jacobian defactors because you have 2 free indexes. You just follow where they are, right? This is in the contravariant position. This one's in the covariant position. And then you just prime everything else. It's that easy. You do the same thing for this piece, right? So now you see these Jacobian factors are the same. So we can just factor those out. And in doing so, you're left with this. Well, what is that? Well, that's just the prime version of this, right? It looks exactly the same, except it's primed, and it's got 2 Jacobian factors matching these 2 free indexes. So that is just the primed covariant derivative, right? You got the covariant derivative, the prime covariant derivative with 2 Jacobian factors. So it transforms according to these rules, then it's a tensor. That's all it means. Okay? Now, here's a logic way to do it. Let's go back to where we did this equation, and we said this piece was the covariant derivative. Let's put that right back in here and look at this equation. So we're saying the partial derivative of a vector with respect to a coordinate is equal to the covariant derivative of this component times this basis of vector. Well, the derivative of a vector is a vector, and a vector is a tensor. We know that basis vectors are vectors, so they're also tensors, right? So there's something called the quotient rule, which says that if the product, let me make sure I get this right. The product of an unknown factor, something, if it's multiplied by a tensor, a known tensor, and it results in a tensor, then that unknown thing is a tensor. Does that make sense? So we know this is a tensor. We know that's a tensor. We don't know that that's a tensor. But because the inner product of these two things is given a tensor, then this is a tensor. So that's the logic way. Hope that helps. See you later.